Hi and welcome to a lesson of partial differential equations. So in today's class, we are going to solve a problem related to heat equation with time-dependent Dirichlet boundary conditions. So in the previous class, we already learned how to solve a homogeneous heat equation using the Adomian decomposition method. Now the problem statement says that LTU equals LXU, where LT means the partial derivative with respect to t, and Lx means the second order partial derivative with respect to x. And the inverse operator LT inverse applied to a function implies that we need to integrate the function from 0 to t with respect to t, and the inverse operator applied on the function with respect to x means we need to integrate twice with respect to x, right? Now we will solve this problem first in the t direction, and then we will see that how to solve the problem in the x direction as well, and we will compare the results, right? Now starting solving the problem in the t direction, we need to apply the inverse operator with respect to t on both sides. So we get this expression. Now this LT inverse LTU means u of xt minus u of x 0 equals LT inverse LXU. And simplifying this expression will give us u of xt equals ux comma 0 plus the operator. Now since we know that we are going to solve the problem by using the series expansion, so therefore first of all we need the u naught term, that is this term u of x comma 0. So this is equals to x plus cosine x. Then for u1 we need to apply this operator, which means integrate from 0 to t by first partial differentiating this function, that is u naught x plus cosine x with respect to x twice. Therefore we get the result as negative cosine x dt, which gives negative t cosine x. Similarly for u2, now again applying the same procedure, so integrate the function by differentiating this u1 twice with respect to x, we get t cosine x dt, so we get t square over 2 factorial cosine x. Now similarly for u3, we will get negative t cube over 3 factorial cosine x. And moving the same way, we can get the nth term. So if we combine all these terms, we are going to get the result for ux comma t. So this will be x plus cosine x, that is the u naught term. Then u1 term is negative t cosine x. Then we have positive t squared over 2 factorial cosine x dot dot dot. Therefore x plus, if we take cosine x as a common, then inside the bracket we have this function, that is nothing but the Taylor series expansion of the function e to the power negative t. So we have the result for ux comma t, that is x plus e to the power negative t cosine of x. So this is the solution for the given problem, and you can also verify the problem, the boundary conditions, and the initial condition as well. Now if we move in the x direction, so we need to apply Lx inverse operator on both sides. So we get this expression now. And for the right hand side, that is Lx inverse Lxu, we will get u of x comma t minus u of 0 comma t minus x ux of 0 comma t. And we already have shown this in the previous previous lesson, that how to find this thing by integrating the partial derivative, a second order partial derivative, right? So this is our right hand side. So if we simplify this and move these terms to the right side, we will get this expression. Now, first of all, we need to identify these functions. So u of 0 comma t is given as e to the power negative t. So this is e to the power negative t plus x times. Now this is ux of 0 comma t, which means it's a function of t. Therefore, we can write it as h of t plus lx inverse ltu. So u naught for this problem will be e to the power negative t plus x h of t. Now for u1, we need to integrate, because this is lx inverse operator, by first differentiating this function with respect to t. So we get this thing by differentiating, and now we need to integrate. So we'll get u1 equals negative x squared over 2 factorial e to the power negative t plus x cube over 3 factorial h prime of t. Now for you to again repeat the same procedure, we will get this as x power 4 over 4 factorial e to the power negative t plus x raised to the power 5 over 5 factorial h double prime of t. Similarly for u3, we will get x to the power 6 over 4 factorial e to the power negative t plus x to the power 7 over 7 factorial h triple prime of t, right? And by solving it for the nth term, now we can generalize this thing. So now u equals u naught plus u1 plus u2 and so on. So that is equals to u naught is e to the power negative t plus x h of t. And then u1 is negative x squared over 2 factorial e to the power negative t plus x cube over 3 factorial h prime of t plus u2 is x to the power 4 over 4 factorial e to the power negative t plus x to the power 5 over 5 factorial h double prime of t and so on. Now to find h of t, what we can do is we can use this initial condition, right? So let's use the initial condition. So we have u of x comma 0. Therefore, we can just write in this way, that is u equals now e to the power 0 plus x h of 0 minus x squared over 2 factorial e to the power 0 plus x cube over 3 factorial h prime of 0 and so on. Now u equals 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial dot 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 plus x h of 0 plus then x cube over 3 factorial h prime of 0 dot dot dot. Now this is equals to x plus cosine of x, that is equals to this thing. Now this part here, that is 1 minus x squared over 2 factorial plus x power 4 over 4 factorial and so on, this is nothing but this is equals to cosine x, this thing here. So it will be cosine x plus x h of 0 plus x cube over 3 factorial h prime of 0 and so on. Therefore, this cos x cancels and x is equals to x h of 0 plus x cube over 3 factorial h prime of 0 and so on. Now we can compare the coefficients. So the coefficient of x is 1 here, so h of 0 is 1 and all other coefficients will be 0. Therefore, h prime, h double prime and so on, they are equals to 0. Therefore, we can conclude that the function h of t is simply equals to 1. Right? So because if we want to find h of t in terms of Taylor series, we can say that this is h of 0 plus t h prime of 0 plus t squared over 2 factorial h double prime of 0 and so on. So all these terms are 0, therefore we will only left with h of 0. So h of t equals to 1 we get. Now therefore we are going to use this thing, that is h of t equals 1. Therefore now what we get here is, let us write here the final result of this problem. So now u equals this thing e to the power negative t plus x times h of t, which means x, and then we have negative x squared over 2 factorial to the power negative t, then h prime of t is 0 because h of t is 1, so this term is 0, this term is 0, so we are only left with these terms where we have this thing, right? So now we have x plus, if we take e to the power negative t as common, so we'll get 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial plus dot dot dot. Therefore, we get x plus e to the power negative t times this expression is of cosine x. So this is the final result of this problem. So here we see how to solve a time-dependent Dirichlet boundary condition homogeneous heat equation problem using the Adomian decomposition method. So that's all for the time being. Thanks for watching the lesson.